Is that right?
Is you all know that we are going to organize the Asian NIR Symposium in the month of December next year. And before that, in order to sensitize people in India and to know about the activities of our Asian NIR Consortium, we are organizing a year-long monthly webinar series. So the first one was organized in the month of November, and it was the webinar was presented by Professor Tsuchikawa, who is the main person in Asian NIR Consortium, and Professor Chung is also is a supporter of us in the sense that he supported us in organizing the conference, but for the first time in India. So Professor Chung is now the Secretary General of this Asian NIR Consortium, and he is a professor in the University of Hanyang University. He has got very rich experience in the field of in research in the field of NIR spectroscopy, chemometrics, and other issues. So we have requested him, and he agreed. So this will be our second webinar series in the conference series, and we are very glad to welcome here. After that, we have one presentation by Professor Saxena of FOSS. So it will be tentatively about 1 hour. So I request with that very small introduction, I request Professor Chung to please start your presentation.
Okay, thank you for the introduction. And my presentation is supposed to be 45 minutes, right?
Yes.
Okay. So let me start with my presentation. So actually, today I'm going to talk about what is important in the calibration in the NIR using the NIR spectroscopy. Okay, and then so in this slide I will skip this one. Okay. So because maybe many people know what is an NIR, I guess. And also I'm gonna skip this one, okay? But I think that this one is important, I guess, okay? So as you can see here, this is a Raman, not an NIR spectra, okay? This is a Raman spectra of the hydrocarbon. Hydrocarbon is like a gasoline or something like that, okay? So usually, you know, the Raman or IR spectroscopy, usually we said it is a fundamental vibration, right? Fundamental vibration. But usually in the NIR range, usually we have a combination as well as overtone band. Okay. So from this range is NIR range. This range is IR range. Okay. This is IR range. So this is the first combination. As you can see here, spectral features are quite narrow. That's good. That's good for the analysis. And you can see this is a combining this peak and this peak together. Okay. And also this is what this one is a first overtone. First overtone means the doubling the frequency. So that means that, you know, this one is a doubling frequency here. I calculate the number. This is the first overtone band. And then this is a combination band. And okay, this is another combination band. This is a second overtone band. Okay. So what is important here is that in the NIR range, you know, the spectral features, I mean, the selectivity means how peak is sharp. So as you can see in this range, 5,000 to 4,000 wave number, the spectral features are most clear. And then if the range is further from the IR range, you can see spectral features are getting broad. Okay, getting broad. So that means that if we want to have a good analysis, Obviously, it depends on sample system, okay? But if the sample matrix is very simple, it doesn't matter. But if you are dealing with the complex sample, I think you might want to use this range for your analysis, okay? So that is very important based on my experience, okay? And also, so this is very important. So, okay, so I will skip this one. Okay, so I think everybody heard the PCA, principal component analysis, partial least square. Okay, so typical method of typical method for the qualitative analysis. This is typical method for the quantitative analysis. If you want to determine some value, I think PLS is very, very popular. So I think everybody heard here many times. I don't want to go detail. Okay. So also in the NIR case, maybe we have many different pre-processing methods. So this is like a first and second derivative spectra. And there are a whole bunch of different types of spectral treatment. Okay, but that is typical. But I think this is a main point here. Okay, so when a path length is fixed, path length is if you want to measure the transmission measurement, okay? Transmission measurement, you can see what if the path length is 0.05 millimeter, okay? You can see you have a very nice spectrum here, okay? But as you can see here, in this overtone band intensity is very, very small, okay? And then if you increase the path length 1 millimeter, 2 millimeter, this peak is getting saturated. That means that the sample is too thick, but you can highlight more in this peak. You can highlight more in this peak, okay? But when your path length is, for example, 10 millimeter, you can see the second overtone combination and second overtone band, but this peak will be saturated. Okay, so that means that depends on your path length of your sample. You can choose. Okay, so for example, if you want to measure the 10 millimeter path length, that means that you're trying to use this band. Okay, but if you're going to use 0.5 millimeter or 1 millimeter, that means that you are trying to more focus on this peak. So as I mentioned before, this range is most sensitive region. So depends on your sample, depends on your sample, or depends on your goal for the accuracy. I think in the NIR range, maybe you might have a choice to use this range. Also, you might want to use this range, or you might want this range. There are three options, I guess. Three options. But among this region, I think as I mentioned before, most selective region is here. Okay. But the problem is that in the many NIR instrumentation, they use optical fiber. Okay, because optical fiber is very, very good for easy sample measurement. But optical fiber itself observe this peak. Okay, so that means that if you are going to use optical fiber in your instrumentation, that means that you have to forget about this peak, which is the most selective one, and only you have a choice of using this one and then this one. So depends on your target analysis. I think you have to be very careful which range you want to use. Okay, so that is the main focus here. Okay, so and also you can see the NIR spectra of normal linear hydrocarbon. So so I don't know, you have many the chemistry or not, or something like that. So I measure the pure sample. Carbon number is 8 to 26. And you can see observance difference is not linear. Okay, so that means that if you have the small molecule, That means that it is easy to distinguish the difference of molecular structure. But if your molecule is getting bigger, the differentiation is quite challenging. Okay, so also it depends on. So for example, you know, if you want to measure the crude oil, okay, this is a very long hydrocarbon chain. I think the sensitivity is getting lower. So in that case, this range is better to use. Okay. So this is what I want to say. So actually, for the accuracy of your measurement, I think 4 important parameters is very important: signal to noise ratio, wavelength accuracy of your instrumentation, also spectral resolution, or sometimes the spectral range. Okay, it depends on. So I will go one by one based on my experience. Okay. So signal to noise ratio, there's a very important parameters. I don't want to go detail. So actually, this is what we have done long time ago. So actually, in the spectrometer, if you scan more time and average more, noise is getting lower. So actually, this is a 100% line. 100% line means no absorption. You can see 64 scans, 128, 192, 256 scans. You can see noise is getting lower. Okay, so if we are going to use 64 scan, error is higher, and if you decrease the noise, error is getting lower. So many people does not think about the signal to noise ratio. A lot of NIR people, they just measure the spectrum and they just run the calibration, PLS, whatever, deep learning, whatever, and reporting the result. Okay, so but I think the instrumentation viewpoint, it is much better to optimize your spectrometer to have a better signal to noise ratio. Okay, so obviously, as I mentioned before, it depends on your application. I think if you want to, measure the water in ethanol, I think it's a 2-component system. It's quite easy. It may not be not important, but if you want to analyze complex sample, I think a signal to noise ratio is quite important. Okay. Okay, so let me go quickly, skip here. So I think my presentation is 45 minutes. Okay, so also wavelength accuracy. That means that, spectrometer, it should have the wavelength should be constant all the time. Okay, so I think the wavelength accuracy is very important. Okay, so, so sometimes the instrument has a calibration using the water vapor. Okay, because if you have an NIR spectrum without sample, you can see water peak. Okay, sometimes you have to check your instrumentation is what? The wavelength accuracy is good or not. Okay, so actually that is an important parameter, I guess. So also, okay, so that is okay, and also let me go skip this one. Okay, also, sometimes, for example, sometimes you have to check your reproducibility of your spectrometer. Okay, that means that, NIR is like always modeling-based techniques. Okay, that means that we assume that analyzer spectrum is never changing. But for example, you measure the one sample today, and maybe it's the same sample. If you measure the next year, same time, is that spectrometer, spectral features are same? Maybe different. Okay, so if the spectral features are changing, that means that your prediction error is increasing. Okay, so you might have to check carefully. About the reproducibility of your measurement. Okay, so this is a long time test ago. So this is actually gasoline spectrum. On the 2000 and 2500 nanometer range. Okay, so I have a circuit company. I don't want to say which company, but circuit company. I have three different instruments manufacturing from one company. One company means a circuit company. Okay, so also this is square. Also Square company. I had three different analyzer made from this company. We measure the same sample together. Okay, so actually you can see in the circuit company, actually here we overlaid with the three spectra, but you can see the spectral features among the three instrumentations are very, 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 very close, right? But in this case, the Square company, even manufactured from the same company, you can see spectral features are slightly different. So slightly different means that model will predict not accurately. So that is quite sure, right? So that is quite sure. So you can see this is a different spectra among the three instrumentation. So that means that I made a different spectra. That means 1 minus 2, 2 minus 3, 3 minus 1. That's why we have three different spectra from the circuit company and three different spectra from the Square company. You can see the spectral difference is quite large, right? So actually, I build a model, and I predict gasoline property. This is actually density of gasoline. Okay, as you can see, a Square company, the predicted value are largely somewhat changing, and the standard deviation is 0.44 to 0.31. Okay, but in that case, the circuit company, you can see the standard deviation of the prediction of gasoline property. You can see much smaller. Okay, so I mean, a lot of people think, you know, they collect a lot of sample and they build a model. Okay, so and then they are examining the accuracy, right? But I think the reproducibility of your instrumentation. Also, as I mentioned before, the signal to noise ratio and also wavelength accuracy. You need to regularly check, see if it is correct or not. Okay, so that is one thing. As a chemist, I want to focus. I want to ensure for accurate quantitative analysis. Okay, so actually spectral resolution. Okay, so actually in NIR there are FT type, dispersive type, AOTF type, or diode array type. You can see, you know, there are many different types of NIR analyzers, and but the spectral resolution is different. Okay, so I test. So actually this is what? This is, I measure the total. Top one is what? High resolution spectra, and bottom one is low resolution spectra. So as you can see here, when you measure the high resolution, you can see it looks two peaks here, but the low resolution, there are only one peak here. Also here, there is a two peaks here, one peaks here. So depends on your resolution. The highlighting the spectral feature is different. Okay, so also resolution, higher resolution is better, but it depends on application. I mean, if you have a very simple matrix sample, I think resolution may not be important. But if you have, again, you know, complex sample, I think a higher resolution is better. And also we have a very detailed peaks here, but the low resolution case, you can see it is quite not significant. So okay, this is a spectral feature between the different resolution. Okay, and so actually we measure the NIR spectra of 4 different wave numbers, 4 different resolution, and then actually we prepared the 55 samples, and we have 25 different hydrocarbon mixtures. Okay, and then we collect the 4 different resolution, as I mentioned before, and the path length is 0.5 millimeter, and the range is 5 to 4,000 wave number. Okay, so Actually, this is our samples. You can see I purchased whole pure components and we mixture. And how many mixtures again? We have a 55 mixture with a different composition. Okay, so actually, this is what we have done, and this is NIR spectra of the normal heptane or something like that. Okay, so I just want to show like this, and then okay, so this is a 2,4-dimethyl pentane. Okay, NIR spectra. Okay, this is every spectrum. Okay, cyclohexane case. You know, low resolution, high resolution is different. So actually, this is a normal hexane spectra with a different resolution. So you can see if the resolution is getting lower, peak is smaller, peak is getting broader. Okay, so I think there is a key issue. There is a key issue you might want to consider. Okay, so this is a highest resolution and second highest, third, and the lowest resolution. Okay, so and then this is a benzene with a different resolution. You can see benzene is actually a unique molecular structure. Usually band is very sharp, right? But as you can see here, when you decrease the resolution, the sharp peak is getting broader, and then the sharp feature, it will be lost. Okay, so that is what happened. So this is actually this is a calibration component and the concentration range, as I mentioned before. So I'm trying to have total paraffin concentration, total normal paraffin, aromatic concentration, normal hexane, something, using the PLS. Using the PLS, I determine those component concentration. This is a maximum minimum concentration range, average standard deviations. Okay, so this is error. This is a result. SCCV is a standard of cross-validation. But as you can see here, when the resolution is a 4-wave number and 8-wave number, the accuracy is quite similar. Okay, and the number is a parenthesis. 12 means number of PLS factor are used. Okay, quite similar. But you can see from the 16, you can see the error is going compared to this column. Error is getting higher, and that means it is impossible to measure. No error. I mean, it is impossible to measure. So that means that, you know, and then 32 wave number, the lowest resolution, you know, the error is much higher. So basically, based on my experience, at least in the NIR measurement, I think you might want to have at least a resolution of 8-wave number. Is quite important. Okay, so you can see same sample. We measure the same sample, but different resolution. You can see error is getting higher from the 16 and 16 or 32 wave number resolution. So that is one thing. That is one thing I just want to focus. Okay, and this is a total paraffin concentration and 4-wave number, 8-wave number, 16, 18. You can see the 32. You can see the correlation is quite similar, but it is getting more scattered. Okay, This is normal hexane, normal hexane. You can see. In the case of 32, you know, you can see like that. Okay, the resolution is not, when the resolution is not great enough. I think that is quite dangerous, I guess. But so something I just want to mention that recently there are many handheld type instrumentation. Okay, so usually handheld type instrumentation, the resolution is not very good. Okay, but practically it has many advantages. Okay, so when you want to use handheld instrumentation, I think you might want to consider trade-off. Okay, so maybe you are losing the resolution, and that means maybe you might losing the accuracy, but accuracy versus practical applicability. Okay, so So the resolution is quite important parameter to consider for your long-term application. Okay. And also this is a benzene case. Benzene case, 32 wave number is quite good. Do you know, as I mentioned before, why is that? Because benzene is very, very, very clear structure. So that means that even 32 wave number, the lowest resolution, still you can notice the presence of benzene. That's why even the lowest resolution, the correlation is quite good. So that's why, as I mentioned before, if you are determining very, very different or very special characteristic analyte versus remained one, in that case, maybe low resolution, use of low resolution spectrometer might be okay. But if you have to differentiate very similar components in your sample system, I think resolution also need to be carefully designed for your long-term reliable application. Okay, so this is a case of for the benzene. Okay, so this is a 2-dimethyl. You can see. This is a 2,2-dimethyl butane. You can see when the 32 wave number, the result is not good. Okay, and also this test is also interesting. Is that actually I prepare very simple matrix. Okay, so normal hexane is a solvent, and the normal hexane and the toluene. Okay, so that means that normal hexane, normal heptane, binary mixture, 2-component mixture. Okay, but the normal hexane, normal heptane molecular structure is very, very similar, very, very similar. Okay, but the toluene and the normal heptane in mixture, in that case, toluene and the heptane is quite different. So that means that it may be easy to distinguish. Okay, and also I changed the concentration 0.05 to 3.0 weight percent, quite low concentration. Okay, so I collect 30 spectra each matrix. Okay, and I perform the PRS for each band. Okay, so I think that this issue. Okay, so this issue is not critically considered in many actual industry application. Okay, so this is a normal hexane spectrum. Okay, this is normal hexane spectrum. As I mentioned before, depends on your thickness of sample. You have 3 choices, maximize your sensitivity. So example, I think at the D band, I will say D band. Okay, in the case of D band, this is a very, very narrow band here, right? As I mentioned before, this range is IR range, and the 5,000 to 4,000 wave number, the closest to IR range, you can see spectral features are very, very, very relatively sharper, right? But if you want to highlight this band, you have to use very narrow path length. Okay, so 0.5 millimeter. Okay, and the normal hexane I measure with a 2 millimeter path length. You can see still is highlighting here. But I think if you compare this one and this one is less characteristic compared to this one. So in that case, if we use a 2 millimeter path length, you can use this one for the your quantitative analysis. Okay. And this one and the B and the A, this is a 10 millimeter path length. So if you enter 10 millimeter path length, you cannot obtain this one, but you can use only this band. Okay, so if you compare this band, this band, this band, you can see from the right to left, you can see spectral features are getting less characteristic. That means that getting more broader. Okay, so this is a normal hexane spectra with 3 different path lengths, thicknesses. Okay, so actually I made a different spectra. Okay, so difference means that I think as I mentioned before, I put normal hexane in the heptane, okay? Normal heptane and hexane. So that means that, as you can see here, normal hexane minus normal heptane, this is a different spectra. The difference is very, very small, right? Difference is very small, right? So why? Because the molecular structure of normal hexane and normal heptane is very, very similar, okay? So that means that if you want to differentiate normal hexane and normal heptane, I think you might need more sensitive, more selective measurement, okay? But in contrast, in toluene case, toluene structure is a lot different from the normal heptane. The difference is very large. In this range, also in this range, also in this range. So if you want to determine the toluene concentration, I think you don't need to consider much about which range. You can use this range, you can use this range, you can use this range, or whatever, okay? But if you want to determine the normal hexane in the normal heptane, I think the accuracy depends on which range is good, which range is good for your analysis, okay? So okay. Also the actually I'm gonna skip this one. So actually this is actually I control the noise, okay? So because our spectrometer from the whole range, okay, the signal to noise ratio of a spectra is different, okay? So I intentionally change the scan number. So when we measure the AB wave, when we want to have AB range, okay, AB range, I scan the 36 scan, and the noise is this level. And so when I highlight this range, C band, which is a path length of 2 millimeter, the RMS noise is this way, and the most sensitive region, I have a 35 scan and the 2.4, then we have RMS noise. So by changing the scan number of each range, I maintain the signal to noise ratio same for the fair comparison. Okay, so this is a result. This is a result for the normal determination of a normal hexane concentration. Okay, normal hexane concentration. As you can see here, when we use the D range, most sensitive region, you can see the error is 0.55, and the second region 0.056. Okay, so you can see quite similar, but when you using the A and the B peak, this range, you can see error is increasing. Error is increasing. So that means that if you're going to use this range, you might expect your accuracy will be worse. Okay, because the differentiation of normal hexane or normal heptane, we need more sensitivity. Okay, more selective spectral features. Okay, but in the toluene case, absolutely the error is lower, right? Because this is the error is about 0.06, but the toluene case about 0.02 to 0.03. That means that toluene spectral features a lot different from the normal hexane. So that means that it is very easy to recognize by PLS modeling. So that means that's why the error is lower. Also, even using the AB peak, which is a 99 and 6500 wave number range, you can see still error is okay. So that is reasonable. Why? Because toluene is quite easy to differentiate compared to normal hexane. Okay, so what I want to do is that, focus is that, especially when you measure the transmission measurement for like a liquid, whatever, you might have an option to use this range and this range and this range, okay? But that depends on your sample. Maybe you can use this range is okay with a 10 millimeter thickness. But if you want to have more selective and more sensitive measurement, I think you might have to go this range. But as I mentioned before, if you want to use this range, fiber optic based spectrometer, we cannot use that because fiber optic itself absorbs the NIR radiation this range. In that case, only you have to rely on this range. Okay, so it depends on your application. Depends on your application. You have to consider proper ranges for maximize the accuracy of your measurement. Okay. Okay, so actually this is a PCA plot. Okay, this is a PCA plot. So you can see that the black circle is the 5 to 4,000 wave number. You can see the most sensitive region. You can see that depends on concentration. So this is just a PCA plot, not PLS model, just PCA representing spectra into two PC component domain. You can see in the case of using the 5,000 to 4,000 range, you can see the variation is large. So that means it depends on concentration. The spectral features are sensitively changing. Okay, but when we using this one, the triangle region, the less selective region, you can see the triangles are gathered together. That means that it is quite less. It is more difficult to differentiate different concentration. Okay. So same, yeah. As I mentioned before, the concentration is changing 0.5 to 3.0 weight%. Okay, but depends on which range. You can see the variation of the score. Magnitude of the magnitude in the variation of the score is changing. So obviously, I mean, obviously, you know, if it is a sensitivity depending, I think that this one is choice. This range is choice. But in the case of a toluene case, as I mentioned before, the normal hexane toluene molecular structure is a lot different. So this range, you know, variation is very large, but still using the 1990 to 6500 wave number region, the triangle region, still we can see the variation. But obviously this is much larger. This one is much larger. Okay. So even we measure the same sample, depends on which range NIR, which range. I think that your accuracy of PLS modeling can be influenced by depends on which area. As I mentioned before, depends on the resolution and depends on the signal to noise ratio. Okay. Also depends on reproducibility of your measurement. So as I mentioned before, so maybe you have to consider many different points. Okay. And also I changed the signal to noise variation. Okay. So as I mentioned, we have 3 ranges here. Okay. So I intentionally increase the signal to noise ratio by 4, 8, 13, 17%, artificially increased. So I'm simulating, you know, I'm simulating the actual case. You know, your spectrometer signal to noise ratio can be slowly worse, right? Slowly getting worse because your intensity of light bulb may be decreasing, or your performance of your spectrometer maybe is decreasing. So maybe signal to noise ratio noise will be increasing. So once again, we increase the artificially RMS noise for 8, 13, 17%, and then this is what happened. Okay, this is what happened. You can see. So this is a 0.08. So this is a previously 0.055, but 0.058. So it's not really. It is not really changing. So that means that because your spectral features are more clear, even a little bit increase of signal to noise ratio, it does not influence a lot. But in the case of using this range, the error was sorry. Okay. The error was 0.56. You can see 0.069. 0.069. That means that error start to increase. So this is reasonable. Also, when we use this range, slight increase of signal noise, you can see error is worse. Okay. So that means that you know, when you differentiate very, very, very small, very similar component, okay, influence of noise is more significant. Okay, but in the case of a toluene case, the spectral features are a lot different. But even RMS noise is increasing, still, you know, the accuracy is not bad, Okay. So there is one thing I want to focus again. You have to choose proper range. Okay, depends on your application. Okay, so this range. Okay, you can use this range or this range or this range. Okay, so there is one thing I just want to focus. Okay, I will skip this one. Also, maybe there are many algorithms to find out optimal wavelength region. Okay, so this is I published a long time ago. There are many different types of wavelengths, finding optimal wavelengths. So maybe you can use the full range. Maybe you might want to use a narrow down. Depends on application. So you have to find out. We have to find out in long run. Okay, so. Anyway, so actually this is a result in this study. You can see, you know, when we use the whole range, the SEP is a 0.85. When we optimize range, you can decrease the error. Okay, you can decrease the error. So I think that's it for the presentation. Please remember, I think one thing I want to focus is that you might have a choice. You might have a choice to use the spectrum a different region, but think about your application. Okay, your application is very simple. Forget about the resolution. But if your application is dealing with a complex sample, you have to think about the spectral resolution, which range you want to use, or signal to noise ratio, or your instrumentation, or something like that. So if you consider that kind of parameters carefully, finally, you will have a very accurate NI analysis. Okay, so thanks for the attention. So if you have, I think I used 45 minutes correctly. Okay, so if you have a question, please ask me. Okay, thank you very much.
Yeah, thank you, Professor Chung, for your nice presentation. Actually, this is really. And it's an eye-opener for us, and we are working in the field of NIR spectroscopy for calibration and all that, and we are struggling with all these issues, this resolution, reproducibility, and the wavelength range also. Just for our students and for me also, just if you can tell us about the signal to noise ratio, what is the typical value that we should concentrate or we should consider?
So I don't know. I mean, it depends on application, I guess. Okay, but I would say, you know, micro observance is better.
Okay. You know, what is the typical range? I mean, that's what I was.
But I don't know. I don't know. I didn't check the other instrument. Okay, so but I think maybe you know, if you going to the instrumentation company, you know, they specify the RMS noise or signal to noise ratio in their specification. And also depends on which range you want to use. Maybe you might want to put more sensitive detector in the target range. Okay, so there might be another way to improve the signal to noise ratio.
Yeah. Okay. So actually, signal to noise ratio depends on the detector primarily. So if the instrument is made, no one can change it. No, this signal to noise ratio. Only one can add.
Yeah, that is true. Yeah. or maybe you might want to use a very high intense source, bright source. So there might be the possibility, I guess.
Yeah, the signal will be more, and noise ratio will be.
Okay.
Okay. Questions from others? I'm seeing some others located here.
Sir, am I audible?
Yeah. Please.
So I have a question about the modeling techniques right now being used in NIR calibration. Professor Chung have rightly pointed out regarding the integrity of the signals and what parameters we should consider. And those are very insightful observations that we need to look into. But right now, what are the different multivariate techniques? Is there any other good multivariate techniques right now available in the recent state of art other than PCA or PLS?
But I think PLS is working very fine, but I mean there are recently there are many different types of modeling, like support vector regression or some neural network based or deep learning based. But I don't know. I mean, if you want to use the deep learning based, I think you have to use the number of samples should be a lot, I guess. But so far, I think PLS is working fine, I guess. And also, PLS is also more explainable compared to deep learning. If you go deep learning, inside is a totally black box, right?
Right.
In the PLS case, maybe it is a kind of black box, but we can show the loading or whatever, something like that. Maybe it is more insightful. What you have done, but at this moment, I think a PLS is still safe way to improve, a safe way to use at this moment. Okay.
And but right now the basic PLS you are saying, right? Now there are many variants of PLS also available, but the basic PLS still works good.
Yes.
Okay. Thank you, sir. Thank you.
Okay, no problem. Thank you.
Yeah.
Any other questions or? Okay, then thank you very much, Professor Chung. Then we'll move on to the next presentation today. We have one presentation from our partner FOSS.
Okay.
Mr. Himanshu Saxena is waiting here.
Okay. So
once again, on behalf of the ANS, yeah.
Okay. So can I go out?
Yeah, it's up to you. If you want to be here, you are more.
So I will go out. Okay. I will go out. Okay. Thanks for everybody. Thanks for everybody. I hope to see you in India next year. Okay.
Sure. We are welcome. We'll look forward.
Okay. Bye.
Sure. Bye.
Okay.
Yeah.
Bye.
Okay. Bye.
But anyway, Seoul was snow in several days ago. I hope the Kolkata is not cold.
No, it's not cold. It's not.
Okay. Thank you. Bye. Bye.
Yeah. Sure. Okay. Bye. Okay, then we now request Mr. Himanshu Saxena.
Yeah. So good afternoon, everyone. Good afternoon, Dr. Rajiv and
yeah, Mr. Himanshu Saxena is the manager of FOSS, and we have requested him to give a presentation on after our technical webinar. So if you can say something on your product and that possible applications that what you're doing in India.
Right.
Okay. So with that, you please start your presentation.
Yeah. So thanks a lot, sir. So first of all, I would like to thank you and on behalf of entire FOSS organization for giving us this opportunity to come into this forum and interact with you guys and then present our solutions. So I'll just request you to Allow me to share my screen. I hope my screen is visible, sir.
Yes, yes, it is visible.
Yeah. Please
Fine.
go ahead.
Yeah. So basically, like we heard Professor Chung talking about the deep insights of the calibration techniques and then the modeling, the PLS, the AN, and all those things. So what I would focus upon is like more from a like a layman user perspective, because NIR is a complex. It's both a very complex and a very like enthusiastic thing. But then the thing in NIR is like one is what is the scope of NIR theoretically, and then second thing is what is more commercially and more industrially feasible. So what we as an organization or like NIR instrument manufacturer focus are is like what are the applications which are more feasible, wherein we can create robust models and wherein like it can be adapted on an industrial scale. So the our focus is not just to kind of develop different applications for the sake of proving that NIR can do some kind of correlation there, but then more to kind of say that yes, this is something where the NIR can be commercially adapted. So that is what I will be briefly talking about, like what all solutions we have, and then what are the application areas of these different models, and why we have chosen a particular like kind of a spectrometer or a particular technology within the NIR domain. So just to briefly introduce myself, I am Himanshu Saxena. I am by background a food technologist and I have done a executive program in sales and marketing from Calcutta. And I've been in employment with FOSS since November 2017. And in my current position, I'm responsible for the feed and grain business at FOSS India and subcontinent, and then also for key accounts. And talking about my overall experience, I am in analytical instrumentation industry for more than 16 years, and most of this time I have spent in dealing with NIR spectroscopy instruments, especially in the food and agri domain. So that was a brief about me, and then moving further, like I'll just touch very briefly upon why NIR on a commercial perspective. So typically why we need NIR is because in an industrial operation, time is money. So everybody wants to save time, everybody wants quick analysis, quick turnaround time, quick decision making power. And that is what the NIR enables the user to do. So that is why this is a technology which has gained a lot of traction over the years. And then we all know there are associated challenges with the wet analysis methods, like the handling of harmful chemicals, the kind of precision which is required, a dedicated and qualified operator staff, and then like large manpower and a much larger footprint. So these are some of the challenges which all the industries want to like cope up with, and that is where NIR kind of offers a lot of benefits. So the major benefits, I think I'll not go deep because the crowd here, I am sure, like knows the basics of NIR. So I'll skip this because you all know that what all the NIR can do. So what I'll focus more is what are the utility segments. So theoretically, NIR can do a lot of things, but then there are certain applications, certain industries where the NIR performance has been proven, where the acceptance of NIR has been there over the years. And some of the areas are like dairy, grain milling and oil, animal feed, and wheat industries like cocoa, chocolate, tobacco. So these are some of the key industries where there is a commercial adaptation of NIR, where there are instruments readily available, calibrated for these applications. So again, that is one of the area where FOSS works. And then FOSS offers online solutions which can support the following aspects: fast analysis, multiple parameters, broad range of applications, accurate and repeatable results, digital connectivity, which is very important in terms of like multi-site operations, where you have like sites spread across geographical locations and you want to kind of integrate them and then make sure that every site is performing to the same standards, saves operator time, reduce use of chemicals, and then easy to operate and use system. So these are some of the key offerings, and this is something which is common across different models and different offerings from FOSS. So now if you go to the FOSS NIR solutions, so this has been the evaluation of our NIR portfolio. So FOSS has been a pioneer in the field of NIR technology, and then we had the initial generations of our NIRs way back in 1985, and since then we have had this dominance in the NIR market. And over the times we have like fine-tuned those technologies, adopted new technologies, and then we have always come up with new innovations. And then currently the product range which we have is largely spread across these three instrument portfolios. So one is like the DS3 range, which is the full range NIR applications, which kind of works majorly for the feed industry, and then like more advanced applications, and then like more diverse applications like chocolate, cocoa, and all, where there's not much of experience and where you require the full wavelength range. Then we have a diode array based instrument, which is more for the oil seed crushing, but then at the same time, it can do like the basic proximate analysis requirements in any industry, irrespective of the sample type. And then we have a dedicated grain analyzer, which is an entry level market offering, which kind of works well for traders, flour millers, and then people dealing into grain trade, oilseed milling, and all. So these are the three offerings. And one thing which is common across all the NIR offerings which FOSS has is like all our instruments have been designed keeping in mind these three key requirements of the user. So one is that we make instruments that are always ready for the user. So we make instruments keeping in mind that the user or the operator should not have to wait for the instrument to be ready when he has a sample to be tested. So all our instruments have minimal unscheduled downtimes, and then these are optimized for quick processes. Second is we produce results which you can trust. So I heard the discussion about different calibration models like PLS is good or ANN is good. So FOSS offers ready to use calibration. So we have global ANN calibrations. ANN is artificial neural networks, and artificial neural networks is used where you have larger databases, larger sample sets. So we have calibrations which include global samples, and then for a lot of products and matrices, we have these global calibrations which can be like kind of ready to use for the customers with a minimal customization, and they produce results which can be trusted. And then smart data management is one of the most important area, because in today's age generating data is not enough. We need to make sure that that data can be easily accessible and it can be integrated with the like overall industrial process. So then only there is a benefit of like analyzing, because if you're not able to use those analysis results into the process improvement and optimization, then that data generation is not useful. So all our instruments are digitally connected, and they offer a lot of smart data management features which help the user to like properly and usefully utilize the data which is being generated by the machine. So coming to the instrument model, so this, as I showed, the first model is the DS3. This we call as opportunity to innovation, and this is a full scale NIR. This is based on a pre-dispersive monochromator NIR spectroscopy. So here there is a light source which emits light, and then like through a rotating holographic grating, we split the light into individual wavelengths, and then the sample interacts with these wavelengths, and then the detector notices the response. So this is like how the instrument works. And then like again using a calibration model and then like algorithm, so the results are then expressed in a layman understandable unit, like be it a percentage value or whatever is the parameter accordingly. And some of the key like capabilities are this, that this instrument can handle different sample types. It can handle whole grains like cereals, pulses, oil seeds. It can handle all kind of flours and powder samples, and it can as well handle all the liquid slurry paste samples like molasses, different syrups, oils, and all. And if you come about the parameters, since this is a full scale instrument, so it has the capability to do a lot more like beyond the proximate. So of course it can do all the proximate: moisture, protein, oil, fat, fiber, starch, but it can also do your amino acid profiling, fatty acid profiling, and much more. Like this is based on an reflectance, and it covers the 400 to 2500 full nanometer like NIR as well as the visible range, because this additionally can also do color. And it's a IP65 approved instrument, which makes it suitable for use at harsh industrial environments. Talking about some of the key applications where this instrument is used, is feed and forage is one of the biggest application, because this is one industry which adapted NIR like many decades back, and this is something which the NIR is like well established in. Beyond that, dairy is another industry wherein like there are a lot of dairy products, and then a lot of critical parameters are kind of pre-calibrated and available. Then meat is another industry where like parameters like saturated fat, energy, water activity, carbohydrate, collagen can be done with the NIR. Then cocoa chocolate is one example wherein we have done some work, and then we have like ready to offer applications. So companies like Mondelez, Nestle, Mars, they're using NIRs for chocolate applications. Then coffee is another area wherein like parameters like sucrose, caffeine have also been standardized on NIR. Again, if you talk about roasted coffee, then different solubles, caffeine, density, color, all these things we have been able to develop on NIR, and these are some things which are offerable with this particular model. So talking on sugar again, like it's a very complex industry, because like you have a lot of different type of intermediaries and byproducts. So, but then we have developed solutions for all, and this is another application where the NIR is like widely used globally. So be it juice or be it shredded cane or be it the bagasse, be it the syrup, the molasses, the raw sugar. So everything can be tested, and there are like of models available to offer on NIR. And then another unique industry is rubber and latex. So here again, NIR finds the application, and then we have developed model for the DRC and other critical parameters in the rubber industry. So we have installations in the rubber industry as well. And these were just few of the applications which can be covered in the scope of the DS3 model. But then beyond that, the scope is limitless. We have also done work in spices. So there are some spices company which are using the instrument for like moisture content, curcumin content, or like other specific nutrients in the spices. There are companies which are using in the snack industry, in the ready to eat foods, and in a whole lot range of applications. So there is definitely a never ending scope in terms of application with this instrument. And some of the critical companies which are using this particular model is like Mondelez, Mars, Terry, Sohana, Jubilant, Amul, Mode, Google. So these are just few of the names which are using, because these are like critical food-based applications. So this is one model, and if we move further to like the feed and forage clientele, then all major industries which are into related to food and the feed business, so they are all like using these NIRs already for many years. Then if we talk about the another model, which is the diode array based model. So this we call as a oil seed crush analyzer, because majorly we target the oil seed industry with this. But then like it is similar in application to the other model. The major difference being that this is something more suited for the proximate analysis, because this uses the diode array technology. Diode array technology is slightly different from monochromator, because here we use the indium gallium arsenide detectors, and these detectors have the best performance in a narrow range. So here basically we are able to use around 900 to 1700 nanometer range. So that is why this is technology which has been developed typically for proximate analysis. So we don't focus on developing amino acids, fatty acids, and more complex solutions on this technology. But then this is a very good and adaptable technology, wherein the application is to do proximate in oil seeds, grains, or flowers, or oils especially. So we have been very successful with this particular instrument in the oil industry. So be it soya or rice bran or different kind of oil applications. So there is what we have primarily supplied this particular instrument, and we primarily focus there. So this is again a IP65 approved system, which makes it perfect for a industrial adaptable environment. And to talk about the applications, so we have done a lot of work with this particular model in oil palm. So oil palm again is a very complex crop, and then the wet chemistry is very tedious, takes like days in kind of analyzing the samples. So the NIR makes the work a lot easier. There are companies like Godrej, 3F, Navbharat, they have all adopted this instrument and technology, and then there's a whole range of byproducts again in this process which can all be tested using this particular model, and then we have available models for that. Similarly, fish meal is another very wide application of this instrument, and here also we have models for like PVB and nitrogen and similar parameters on NIR. And soya is another important application wherein you can test the seed, you can test the DOC. Rice bran is another application wherein there's a lot of adaptability and existing references for this particular instrument. Fish oil is another area. So all these oils, basically you can do iodine value, peroxide value, saponification value, free fatty acid, moisture, phosphorus. So all these parameters which otherwise would take a lot of time and effort can be done in a single analysis with the NIR. And then the thing which is most important is that this work has already been done and the instrument is proven to do that. So there's not like something which has to be done from a scratch. If somebody has to use FOSS NIRs for this application, already there is at least a starter calibration or a starter model available, which can be further like improved using the local data. So these are the typical list of parameters. So if you talk about the oil seeds, then oil, protein, FFA, moisture are the key parameters. If you talk about de-oiled cakes or meals, then protein, fiber, oil, moisture, acid insoluble ash. And then if you talk about the oil parameters, then FFA, iodine value, peroxide value, sedimentation, moisture, and then other parameters. So all this is in the scope of DA1650, which majorly goes in the oil industry. And then we go on to the last offering from FOSS, so which is like more of entry level NIR offering from FOSS, which is typically like for grain analysis. So this is something which is suitable for grains and flowers. So we can test all kind of grains, wheat, barley, corn, all kind of oil seeds, beans, pulses, and then we can test the flowers also using this flower model as well. And then the typical parameters here are moisture, protein, oil, starch, wet gluten, fiber, ash, and you have the flexibility to do additional test weight, which can be incorporated with the same instrument. And this is based on the transmittance technology, because here we are majorly testing grains and those samples you need like the shorter wavelengths, and that is why the instrument uses 570 to 1100 nanometer range, because there you have the high energy shorter wavelengths which can penetrate the grain samples. And again, this is a IP certified instrument, so which again provides you dust and moisture protection. And the major application for this instrument comes in the grain milling and trade industry. So this can be like wheat and flour milling, it could be rice milling, it could be like the distilleries, the grain based distilleries and breweries, and it could be like starch manufacturing. So all these industries, seed companies, and then government research projects. So all those kind of customers have adopted this instrument very well. And as I said, that the whole range of cereals and oil seeds we have experience of doing on this, including some of the de-oiled cakes and flowers of those samples. And these are some of the critical clientele in this. So many state agriculture marketing departments have adopted this technology. So if you talk about states like Rajasthan, so in each single agriculture market yard, there is this instrument which is used for like scanning and the initial trade. Whenever the farmer is bringing the produce to the markets, all the produce is getting tested on these machines, and these machines are linked with the government enam portals, and then like all the reports are getting uploaded on government portal, and then all the auctions and then the payments to the farmers are being done on a fair price basis using this technology. And then a lot of private companies like 3F or Adani or Kalam Agro, Parak, they all have adopted this instrument very well. So this was about the bench models from FOSS. So these are the three different bench models which suit different application areas. And then NIR is now also uh, popular in the process because we have the online and inline NIR model. So this is something which directly goes onto the manufacturing line. So if any manufacturing is going on, if you want to like monitor the product directly on the line, so then FOSS NIR can be like installed, and it can be attached to the plant control system so that it can immediately detect the product, and then like if there is any like out of spec product on the line, it can immediately connect to the plant hardware and software to kind of take the corrective action. So this is something which is still a very new concept, at least in India, but then this is something which is gaining a lot of traction and then lot of interest from the market, and I'm sure like 10 years down the line this would be a common phenomena, just like bench NR instruments are today in India. So that was about a brief overview of what NR models are commercially available from FOSS side. So if you have any questions around this, please feel free to ask.
So, yeah, am I audible?
Yeah.
Yeah,
Please.
yeah, please.
Yeah. So the instruments those you have, they come with your inbuilt calibration done, or we have to first procure the model and after that we have to calibrate the sample.
Uh, it depends on the application, sir. So, like the applications which I mentioned, so those are the applications wherein we have models. But then, and those, if like your application is within that scope, then of course it comes calibrated for that. And if it is something which is new to NIR, for which lot of work has not been done on an industrial level, then we have to work with you to develop the calibration. But in any case, we have to do some validation at the customer end.
Okay. And regarding, let us say, I have calibrated an instrument. I need to, transfer that calibration to some other instrument, because every instrument is a little bit different, right? I mean, even if your model also we consider uh, different instruments with the same model number, they might be different. So, do you have any provision for calibration transfer, etc., or do we need to do that?
No, calibration transfer can of course be done, but then it would be restricted to like FOSS instruments. So calibration from like one generation FOSS instrument can definitely be transferred to another generation FOSS instrument. But like if it is some other NIR instrument, then it cannot be done because like the file formats are different. Sometimes the optics is different. Sometimes the technology is also different. And then the model technique is sometimes different. Like if we have an NN model and then like it cannot be made into a like a PLS model, or like if we have developed a model on a monochromator system, so then it cannot be used on a FT-NIR system, for example. So those are the limitations, but yes, within FOSS instruments, definitely we do that because like there are customers who like 10 years back, if they purchased an NIR from us, like a different model, and today if they're going to the latest model, so all those calibration libraries are like compatible.
And typically, how much accuracy can FOSS guarantee for, let us say, a specific product? No, it's a very broad question, but still just asking. And what is your
Yes.
benchmark?
So this is like in my 16 years of career, I would have heard this question at least 1600 times. So because this is the first question which every customer is interested in. But then again, the point is that the accuracy and everything in NIR is largely dependent on your reference. So NIR can never be better than the reference because we encounter customers who are using like those, if you have seen like those, you get moisture meters in the market like in 5,000 rupees. You can just pour the sample, you get some moisture idea. So they want to use that moisture meter and they want to calibrate the NIR with that, and then they want a precision of say zero 0.1 on the NIR. So that is not possible. But yes, NIR will always be as good as your reference. So if your reference is 0 0.2, NIR can definitely be 0 0.2.
Okay.
And on the repeatability, in fact, the NIR will be much better. So if you're doing the same sample on the NIR 5 times, then you will be getting a much better precision as compared to running the same sample 5 times on the wet chemistry. But if you compare the NIR with the wet chemistry results, so then first of all, the wet has to be like uniform, because many times what happens, you develop a model using one set of wet chemistry, and then when you are comparing the result, you are comparing it with another set of wet chemistry. And again, if you compare both those wet chemistries, there'll be a significant difference between those. So all these things have to be taken into account. So as such, NIR is not something wherein we can say that there is accuracy, we can be defined in terms of a number. Any more questions from anyone?
Okay. Any other questions?
Yeah, actually, I have some. So when you have a portable instrument, let us say site, something you have to carry to the site. I mean, what precautions do these instruments have for portable instruments or inside instruments? I mean, there could be ambient effects and ambience effect, environmental effect, dirt, dust, pollution. What I mean, provisions are there for all these factors?
Yeah, so if you talk about portable NIR, so first of all, this is something which is picked up of late, and then there are a lot of companies now offering that. But then some points to critically consider is, one is the sample presentation, because like when you have a portable, the sample presentation is not uniform. In the bench instrument, you have like a dish, or in any way, like there'll be a standard sample presentation, so every time the sample is presented in the same form. But if you have a laser based or a portable system, the sample presentation will not be uniform, which will have an impact on the performance. Secondly, I think the vibrations is something which needs to be considered in a NIR technology, because vibrations will have an impact on the optics performance. And then about the dust and this thing, so of course light is concerned, because like where you are keeping the instrument, and then if it's under direct sunlight, and then the temperature again may have an impact depending on like how controlled is the hardware. So for example, if you talk about FOSS instruments, so we have all these provisions. We have IP65, we have like a cooled spectrometer, and then we have all those things, which is like not possible to incorporate in a portable instrument, because portable instrument will typically be a sensor. So therein, standardizing all these things becomes a challenge, and then eventually it impacts the performance of the system.
Okay. Okay. Thank you. Thank you.
I have a question. Can you provide us the pricing range of the different instruments you showed today in the Indian market, Indian context?
Yeah, I can give you a brief idea. So, for example, the grain models, which can do grains and flowers, the Infratech one, they'll be roughly around 13-14 lakhs plus GST. And then the middle level, the diode array will be around 35 lakhs plus GST. And then the topmost model will be around 45-50 lakhs plus GST. So that is like a broad range. And then again, it depends on the application. So if it's a single application, or if it's multiple products, because this calibration development, everything is also a part of that. And then these calibrations also like have associated costing and all.
Can you tell us about the pricing of the in process models you showed? Have you?
Yeah, in process would be like, again, depend in process. It's difficult to say like price, because it's not only about the sensor, it's about like the installation also, because where in the process you're actually putting that instrument makes a lot of difference in the pricing. But roughly, like if you talk only about the sensor, so it will be like somewhat similar to the like bench instrument, like 50-60 lakhs. But then again, the final cost depends on the installation actually, what point of the process you are like actually installing it, and then what all connectivity features and those things are add-ons to that, because in process there are a lot of add-ons.
Okay, okay. Thank you. Thank you so much.
Any other questions?
Yeah, I have one small question.
Yes.
Yeah, am I audible?
Yes, please.
Hello,
Yes.
yeah. I think that you have shown that you've done with several different compounds in this one. So you've done with caffeine also. So in which product you've done for caffeine?
Caffeine would be mainly in coffee, sir. In coffee we have done, and also in tobacco.
Okay. And so have you done anything on tea?
Tea, we have not done anything on a industrial scale, but I'm sure like if coffee can be done, so tea also can definitely be done, because the parameter is same, so it can be done. Because see, the problem is like as a commercial organization, we will indulge into a application only when we have like a potential buyer for that, because we like are not into research, so we'll not develop applications on our own. So it's all like our development process is all industry driven. So if we have a potential buyer for a particular application, then we invest in developing that calibration and that application. But then tea is something which definitely can be done.
And I think you have done the caffeine estimation you have done with on a dry powder, or I mean the instant coffee, something like that, on a dry
Yeah,
powder.
on roasted coffee.
Okay, I get it. So what about, say, do you have any software or any for moisture? Because there are moisture in tea, say, so because we know that moisture has an interference in NIR calibration. So if we have a wavelength in both near the moisture range, so do we have have you done anything on wet? I mean wet molecules or wet stuff, something that contains water.
We may not have done it this, because coffee beans also we have done. So in green beans also we have done sucrose and caffeine. So, but then again, these applications would have been done on like relatively smaller sample set and like a smaller group of customers, unlike applications like animal feed or grain, which like has been done on a much wider data set. Because if you talk about grains, then there are thousands of customers using the instrument already, so that those sample data sets are much bigger. So like some of the common grain calibrations could be like 10,000, 20,000 samples, which will not be the case for like coffee and these kind of things. So these will be maybe 400, 500, 100 data sets. So, but then yes, green beans also has been done. So moisture in green beans, and then caffeine again has been done on this. So it's both on roasted as well as the green beans.
So how was your results, accuracy of results in for green beans where there is moisture?
So
Because
I
we have a
do not
problem with
have,
moisture, the moisture
yeah, but
creates a lot
that
of
is
interference.
That is true, but then I think moisture is something which can be like detected easily with NIR, and then you can always kind of do the other analysis on a dry basis, accounting in for the moisture. So as such, I think I do not have the figures with me right now, but then I think the SCPs and all the R-square values which we got for those applications are decent. So they must be in the range of more than 0.85 or so.
Okay, thank you.
Thanks.
Yeah. In any other questions? Okay, then I have just one question. The earlier you were using this monochromator based instrument, and after that you have switched. You have also the diode array based instrument. So I believe the diode array based instrument, the resolution is I mean low compared to the monochromator based, isn't it?
Yes.
If I've understood correctly.
Yeah, so basically the reasons are is again like as Professor Chung was also highlighting, because it's not just the signal to noise ratio or the resolution, so it's a mix of everything. Because like again for the industrial perspective, it's also the price of the instrument, and then like the hardware associated, because when you use diode array, you use indium gallium arsenide detectors, and then indium gallium arsenide detectors have a have a high sensitivity in a lower range, so like around 900 to this. So they at there they can give a better signal to noise ratio even at a low resolution. So it's a mix of the sensitivity of your detector. So what happens, the signal to noise ratio is actually something which many times is more important, especially when you are dealing with the diode array instruments, because even if you have a lower resolution and if you use a detector which has a very high sensitivity, so then you can improve your signal to noise ratios there. And again, it depends on the application which you are targeting. So if the applications which we are targeting are like more approximate, because what happens, on a industrial scale, it is not possible to do everything in one instrument. So we of course have one instrument which can do everything, but then the cost of that instrument is too high
Very high.
for everybody to
Correct.
kind of incorporate it commercially. So that is why we need to kind of have, because somebody who just wants to do oil seed and oils, and who just wants to do moisture protein fat fiber, so there the resolution requirement is not that high.
Mhm.
So it's always application based approach, and that is why the companies come up with different models. For that, I focus on three key models, but then we have dedicated models for meat, we have dedicated models for dairy, because again those products have a specific requirement. So you don't actually require the full wavelength range, or you don't actually require that high resolution for that particular application.
Resolution. Mhm. Yeah, yeah. Okay, I think it was really a very, very nice presentation, Mr. Saxena, and most of our, I mean,
Thank you, sir,
yeah,
for the
Dilip,
opportunity.
yeah, Dilip has got some question. If there is overlapping of peak, how will you get result using Mr. Saxena, will you open the, yeah, if there is overlapping of peak, how will you get result using machine learning? Or
Overlapping of peaks. This overlapping of peak, how will we get there?
Actually, I think what he is trying to say is that, as you said, that you are using artificial neural network. So what he is trying to say is that if there is like overlapping of wavelengths, like two there is
Understood, understood.
intersecting
Yeah,
thing.
yeah. So basically, when we develop models, especially in the artificial neural network, it's not just one wavelength absorbance that we are using in the algorithm. So it will be like a multivariate thing. So you use am I audible?
you are audible? Yes, you are
Yeah,
audible.
fine. So basically, so as I said, it's not just absorbance on a single wavelength that is used, because as we know that there are overtones always. So that is something which precisely we use in the diode array model, because there are several parameters which do not absorb at all in that way. So, but then you can always, you may not have a primary peak, but you have a secondary peak in that particular region. So in case of overlapping, it's like when you're using like multiple peaks, so then you can basically take care of that, and you can make more robust models.
Okay, thank you. I think Dilip, you can also unmute yourself and talk if you want. Or
There may be some network issue with Dilip.
yes. It may be so.
I have understood.
Thank you for your answer,
Yeah.
Mr.
Yeah,
Yeah.
thank you, sir.
Okay, so on behalf of the organizing committee of ANS 2024, we thank you very much, Mr. Saxena, for your presentation.
Thank you, sir, for
And we hope
giving
to
us
have a
this
good
opportunity. Yeah,
yeah,
we
for
look
organizing
forward
this,
to working with you.
yeah, for organizing this conference also. We'll have this pre-conference webinar series in every month. We'll have one webinar on NIR, and I request you that you can also pass this, you please join the other webinars, and you can also pass this information to your clients, so that they
That
get to know.
definitely.
Because this NIR culture, what we feel, this is very much needed to be promoted in India. It is there, but it needs to be promoted. There are a lot of opportunities and a lot of
Definitely,
applications.
definitely, there are a lot of opportunities. And one thing which I see is, I've been working with NIR companies last 15 years, and then like just 6-7 years back, we used to like visualize the overall NIR market in India as like say some 50 units, and today FOSS alone sells more than 200 NIRs. So the overall market has now increased to up to around 300 units just from like 50 few years back. So this is definitely something like which is bound to kind of increase in terms of acceptance in the industry. So it's something like you have picked up very well, and I think spreading the awareness about
Yeah,
this
yeah,
is
and this is the first time.
something very good.
Yeah, yeah, and this is the first time this ANS will be organized in India. So we need the support from you and as well as from other companies so that this can be promoted.
Like,
We
sure,
can
sir,
invite many
we'll
persons
do
from
our bit.
outside India. Okay, thank you very much, Mr. Saxena. So we'll close the session today. I will wait for the next webinar in the next month, in the
Thank
new
you.
year.
Thanks, everyone.